All right. Um, Welcome back, everyone, for the last session of the e-learning modules. The last session will be given by Bart Simons from the Royal Military Academy. So he already made a general e-learning session dealing with energetic materials. And now, today, he will introduce us on the analysis of some explosive and propellant residues, with the intention, of course, to go through the analytical procedure. And then for those who will come to Belgium within 2 weeks, there will also be one day that you will be in Brussels in the Royal Military Academy to follow this training. So, having said that, Bart, please, the floor is yours.
Well, thank you, Christophe. So, as you said, I will just talk about the analysis of three compounds that were selected among all the energetic materials, and I think it was a good choice, as I explained in my first presentation. So these are the references, a lot of text, but basically some ISO standards dealing with soil quality. One has been seen before, I think, about determining the amount of water and dry matter in the soil. And then the three others are specific for the detection of explosives. The one is for HPLC and an ultraviolet detection, which has quite high detection limits. A second one based on GC, but we mainly focused on the third one, which is liquid chromatography and MSMS as a detector, because the limits of detection are much lower than for the part number one. So, but we will come back to that. So these are the references, and this is the content of what I will be talking about. I guess it's mainly similar to other presentations of the same kind, only the molecules are different and the procedures might be slightly different. So we'll talk a little bit some details about the initial steps to take to prepare the samples, determine the water content, and then some more details about the extraction as we performed it in the lab and the analysis as we did it for these three specific molecules of explosives. So in order not to show this content slide too often, I will focus first on the three first topics because they are only 1 or 2 slides long. So storage, it's not so complicated. The colder the better if you want to store a soil. As the soil arrived at the academy without being frozen, I think it was not so useful to freeze it again. So we stored all the samples as they arrived in the refrigerator at 5 degrees. We did the same after sieving. We will see about that on the next slide. And then the solutions after the extraction, just for safety and also for practical reasons, were stored in a freezer at minus 18 degrees. At the right, you see a picture that I showed in my first presentation, which is basically the reason why you should store soil samples at as cold as possible, at least from an explosive point of view. So this was the concentration of TNT in a soil at room temperature. It was quickly degraded by all kinds of organisms and mechanisms happening in the soil. So if you want to keep your proof visible in the soil, you have to store it in cold temperatures. At least a refrigerator, but a freezer is even better from that point of view. Sieving or homogenizing, so that's the second step after storage. Each sample, one at a time, has to be sieved with a quite rough sieve. So the procedure foresees an aperture of 2 millimeters, which means that you only take out the really relatively big chunks. So this is what the system looks like. I can show a little movie, but it's really a simple tool. So it's a sieve, it's a shaking machine. And so you just screw everything fixed. It shakes for quite a short time because it doesn't require such a long time. And then you have two fractions, of course, the fraction that passed through the sieve and the fraction that remained in the sieve. All particles above 2 millimeters remain on top, and so that is just a shaker. You can put several sieves on top one of another, but we didn't. we didn't have to do that. So my colleague was making a lot of noise while I was talking. And so basically we put all the material larger than 2 millimeter back in the original storage can, and the other part, the sieved part smaller than 2 millimeter, we put it in a glass jar. We were supposing that this was enough to homogenize the sample, but this appeared to be a little bit too optimistic, as we will see in some of the next slides with some results that we achieved. So basically, we thought it's mixed enough. Everything has been mixed well enough to have something homogeneous, but that was not always the case. And afterwards, of course, it's important to avoid cross-contamination from one soil to another or from one sample to another. So there's quite a procedure to wash the sieve first with water, then with acetone, and then have finally a clean sieve again for the next sample, so that one explosive in one sample doesn't contaminate all the next ones that are sieved in the same sieve. For the water content, I guess this is also a story that you heard before, because we're not the only ones who need to determine the water content. Why do we do it? Because the answer in terms of quantity of explosive was asked per kilogram of dry matter. The soil that we extract is not completely dry, so first we have to know how much of the soil mass is dry matter and how much is water. I think most of the samples didn't contain that much water. So basically we take a glass jar as it is foreseen in the procedure. We put it in an oven at 105 degrees just to dry it for 3/4 of an hour, 45 minutes. We let it cool down in a desiccator in order to make sure no humidity comes back on the glass jar. We weigh this empty jar, and this is the M0 that we will encounter in the formulas. Then we add some of the moist soil into the glass jar. We determine the mass. It's called M1. We basically aim for something like 20 grams. And then we go back in the oven for first time for 12 hours. Then we weigh again, and we see how much is M2 different from M1. And the difference in mass is, of course, the amount of water that has evaporated. We do it again, now this time for 4 hours. And then we measure again. We have a mass M3 now. And we do that game again of putting it back in the oven and weighing until the difference between two successive measurements is less than 0.1%. For most of the samples, after 1 or 2 cycles, it was more than enough. And then you obtain 3 masses. You have the empty jar, M0. M1 was the moist soil in the jar, and M3 is the jar containing the dry soil. All the water is gone. And then there are some formulas in the norm that allow you to calculate the fraction of dry matter, or the mass of dry matter if you multiply by the total mass of soil, and the fraction of water in that sample. So that's the first step to take, and that's one of value that we will take into account in the final calculation of the concentration. So these were the first 3 parts, basically preparing some samples and then determining a first parameter is the water content. But of course, the most interesting part is the content in energetics, and that's the first step that we have to do there is an extraction. The procedures, both or all 3 of them, so the UV, the MS with liquid chromatography, but also for GC, allow the use of 3 different types of tools. There's the socklet extraction, there's a mechanical shaker as it is in the picture. This of course is the tool for the socklet extraction. And the procedure also foresees the use of an ultrasonic bath. Now we had the luck or the unluck, as you want to consider it, that our ultrasonic bath was in having technical issues. Let's say it had to be replaced when the samples arrived, so we chose not to use that. But we did use the mechanical shaker and the socklet extraction. Before getting more into detail, I would just like to spend a few words on this graph. This graph was part of the procedure that we used. And it's basically a comparison between 2 solvents, methanol and acetonitrile, that can be used for extraction of energetic materials from soil. And so the people who did this study basically saw for most of the explosives that the use of acetonitrile or methanol was basically the same. And the way they did the extraction was by using a mechanical shaker. However, if we see on the left, the two molecules that are quite similar, HMX and RDX, they have a very low recovery when using methanol. So they say if you want to recover RDX from the soil, you have to use acetonitrile. That was a little bit worrying for us, but because when we did tests with acetonitrile as the extraction solvent, we noticed that for calibration, for quantification, it was really difficult with the method as we are used to using it. So we try to verify these results using our own extraction and our own tool. And this is basically what we noticed for RDX and for TNT. So 21 and 48 are the number of two of the samples that arrived from Ukraine. MS stands in this case for mechanical shaker, acetonitrile as the extractant or methanol. And so we compare RDX and TNT. And indeed, as the results of the previous slide, we see that if we use the mechanical shaker and we use acetonitrile, we have more RDX that is extracted than using methanol. So basically a confirmation of the previous slide, although the difference is not so very big. For TNT, we see that the results are never exactly the same, but we don't lose anything by using methanol instead of acetonitrile. And then we did an additional test because, as I said, acetonitrile, it would have caused some problems and a lot of working on the procedure as we are using it now. We compare these results to the use of methanol as we are used to using, but using the SOxLET extraction. And then we see that by using the SOxLET, it seems to extract the molecules more effectively than the mechanical shaker. So instead of using the mechanical shaker and acetonitrile, we used SOxLET with methanol, and we all more or less confirmed that we don't lose any RDX in our soil. So this is basically what we try to do and try to verify if using methanol was still a viable solution. And it turned out using SOxLET that it was. We did use the two types of extraction, although the mechanical shaker led to some maybe not so good results for RDX. We also had to look for TNT and DNT. And in all honesty, the mechanical shaker is a lot easier to use than the SOxLET apparatus. First of all, we can put a lot more samples on the shaker. We can only do 6 SOxLETs simultaneously. So we did do both extractions for all the samples. So what I have prepared now are a couple of slides to show how a SOxLET extraction works, how the mechanical shaker works. I absolutely don't mind running through the slides and explaining what's on it, but if that is the 5th time that it is shown this week, just warn me and then we'll skip to the next part. It's probably the same for every procedure that requires the use of the SOxLET tool. So basically the beginning of the preparation of the sample for the SOxLET begins by taking a thimble in cellulose. And so we weigh the empty thimble, and then we fill it with some of the soil, one of the 39 samples that arrived from Ukraine. And then, of course, we determine the mass of the thimble and the soil to determine the mass of the soil that we are using for the extraction. This is an important number to take into account in the final calculation. And we try to aim for about 20 grams. It's never exactly 20.000, but we try to aim something around 20 grams. Then we take the thimble with the soil, we place it in the apparatus, and then we put this part of the glassware onto the round bottom flask, which is placed in the heating unit. And then finally on top, we place the condensation system. So we have 6 in a row, and there's water, cold water flowing through all of them. And so we can do 6 extractions at the same time. In the flask below, we put 25 milliliters of methanol. And so then we just switch on the system and it starts operating autonomously. So it's a quite, I think it's a nice invention, although it's simple. Someone had to invent it someday. So this is the way it works. In the thimble here, in gray, we have the soil. In brown, that contains a lot of matrix, which is not interesting for us. And analytes, and in this case, the analytes could be RDX, TNT, or DNT. And so the principle is that you heat the solvent. Usually it's quite volatile, the solvent, so it doesn't require a high temperature. And it starts evaporating and the vapor rises and it rises through the tube on the side of the system. And it comes into the cooling system where, of course, the temperature decreases below the boiling point, and then the gas, the vapor of the solvent will become a liquid. And the liquid drops, they fall into the thimble, and the thimble slowly fills, and beside, parallel to the thimble, there's also a little system here that, of course, because of the corresponding I don't vessels, or I don't know exactly how to say it in English, but these two levels of liquid are always at the same height. And at some point, when the thimble is almost full, we will reach the top of this little system. And at that point, everything that is in the thimble and in this system will empty into the flask again. It's not solvent anymore. It's solvent that has passed through the soil and that has taken some of the molecules with it. And so we do a lot of cycles, each time vapor coming up the system, condensation, drops going through the soil, taking with them some of the analyte molecules until this thimble is full, and then there's an overflow, making sure that all the solvent and the extracted molecules get back into the flask. And so you can do that for hours. There's no loss in solvent in principle. And so this system can run, let's say, eternally if you have a lot of time. And so each time that the solvent is running through the soil, it takes some of the molecules with it. And then the hope is, of course, that after many hours, all the molecules have been extracted. And as you see, there are only balls left, the circles representing the matrix, and all the analyte is in the solvent now. And then we can determine the amount of analyte, the concentration of analyte in the solvent. So basically, this is the system as it works in theory. This is what it looks like in practice. So this is a picture of a running system. This is the thimble. It's of course it's wet because of all the liquid solvent that has passed through it, and it contains the soil that is visible from more above here. And then at this point, we see that the level of the liquid in the thimble is more or less here. So it's not full yet. So we are, let's say, 3/4 of a cycle far. In this picture, it's more difficult to see, but the level of the liquid is more or less here. So that means that the thimble is almost full. And then when the thimble is full enough and the liquid, you can more or less see here the level. So we are really at the limit of where the thimble is full. When it is full, then we have the overflow and hop with the different up vessels that are communicating. The whole thimble is emptied, and we can start a new cycle because most of the solvent is back in the flask. It will be heated again, the vapor rises, and so on. So this is a system. If you follow the procedure, it takes about at least 16 hours. So basically we start it in the afternoon and we finish it in the morning, and it runs overnight. Well, we've had one occasion where there was a leakage in the water and we find the lab underwater, but okay, that's part of the game. 50 milliliters of methanol initially. Maybe I said 25 in the beginning, so we used 50 milliliters. 20 grams of soil, 16 hours, as I said, and usually in this kind of system, it takes at maximum 15 minutes. So that means that you do 4 times 16 cycles at least in your 16 hours, which provides a lot of opportunity for the solvent to extract the molecules from the soil. So it's really a nice invented system. And then there's some final manipulations. So after 16 hours, when you come back, you find the round bottom flask in the heater. There it contains methanol, and if you switch off the heat, all the vapor will condense, and then you find your methanol back with analyte, hopefully. and all the other molecules that have been extracted by the methanol. So not only explosives are extracted, but also other molecules that are soluble in methanol. The next step is to take that flask and heat the methanol again. And so we let part of the methanol evaporate until 10, 15 more or less milliliters is left. And then we pour it into another recipient. We rinse the flask with methanol in order to get as much of the analyte as possible. And then finally, we fill that concentrated solution up to a volume of exactly 25 milliliters. And then we filter it to make sure that no pollution, no big particles are in the solutions, to make sure that the column of the liquid chromatography tool will not be blocked by big particles. And then we have 25 milliliters of extract solution with or without explosive, depending on the sample. And that's what we store. Now, there's one more thing that we did because of a discussion that we had. If someone was asking if we evaporate the methanol after the Soxhlet extraction, are we sure that none of the explosive molecules are leaving the solution? Maybe it's not only methanol evaporating. So we did a couple of tests where we had a known concentration of a analyte in methanol. We heat the methanol so it evaporates. The volume, of course, decreases, but when we determined the concentrations afterwards, we did not notice any significant loss of analyte, meaning that if we have a certain mass of let's say RDX in the methanol after the Soxhlet extraction, and we reduce the volume of methanol, there's no RDX leaving that solution. So we are not losing any analyte, we're just concentrating the solution by evaporating the solvent. So that's for the Soxhlet. The mechanical shaker, it's a lot easier. Right? Basically, you just have to take one glass bottle, you weigh it empty, you fill it with more or less 20 grams of sample, you determine the mass exactly of the amount of soil, of course, inside. We add, in this case, 20 milliliters of methanol, and then we place it on the shaker. It's something I think Christophe also showed a picture of it in the introduction that he gave about these presentations. So basically, it takes 16 hours as well. In our case, at 135 rounds per minute, that the machine is turning at a certain temperature that we try to keep fixed. Very simple. You can put a lot of jars on it. They are all shaken and extracted at the same time, so it's a lot less intensive for work than the Soxhlet extraction. But for those who will be joining us at the Academy, we'll do a little bit of both, of course. And you have to know how to launch a Soxhlet extraction, how to deal with it. So we will launch some of them the evening before you come, so you can start one and you can end one at the same in the same day. We will play a little bit with the shaker. We probably will start some samples before you come as well, that they are finished when you arrive, and then you launch some. But this is basically a tool that is very easy to use, with the disadvantage for RDX and methanol that we saw in the beginning of the presentation, of course. And this is the result. So as I already said, and as it's on the slide, so for each of the samples, we did one mechanical shaker extraction and one Soxhlet extraction. Then we launched the analysis. If we found something, just as a confirmation, as of the positive indication, and also for the amount of explosive that we detected, we did another Soxhlet extraction. So for all the positive samples, at least 2 Soxhlet and 1 mechanical shaker extraction have been performed. For those that gave a negative result, only 1 of each has been performed. And then we have liquids. Some of them contain a lot of, let's say, pollution, in the sense that it's not a transparent solution. There's something coloring the solutions. Other soils are more transparent. So it depends, I guess, also a little bit on where the soil has been taken in your country. And then we store these in the freezer, as I said before. And then now a few words about the analysis. So LC is liquid chromatography. That's the first part of the tool that we use. Mass spectrometry is the second part of the tool. And then a few words about some things that you have to do to get a numerical result, and a few of the challenges that we had to face, because I have to admit that this amount of analysis of soil extraction was kind of challenging for us, because we are not used to doing that much soil analysis in such a short amount of time. So as we're only busy since 25 minutes, I propose we just continue without taking a break. Analysis, as I said, liquid chromatography and MSMS, it's a tandem mass spectrometry. So let's look a little bit more into detail at these two things. First of all, the LC, LC liquid chromatography. I guess I'm not the first one to tell you that chromatography is basically a separation process. The aim of the LC in this tool is to separate all the different molecules that are in the methanol from another, so that in the beginning we have methanol containing different molecules, and at the end of this chromatography process we have all the molecules separately. And so there are a couple of figures on this slide that explain how it works. Again, I don't think it's the first time you hear it. But in chromatography, we have columns, and for the liquid chromatography, compared to the GC, it's a quite thick column, although it's still not so thick, and it's quite short as well, of course. And it contains what we call a stationary phase. These are particles that do not move, they stay fixed. That's why they call it the stationary phase, of course. And through this column with the stationary phase, we will push what is called the mobile phase. And in liquid chromatography, of course, this is a liquid mobile phase. And at some point, we will inject the mixture, that is the solution from a couple of slides ago that we obtained after extraction. And in that solution are different molecules. And the way we use chromatography, it is completely based on polarity. Chromatography is always based on some kind of affinity that molecules have for the mobile and for the stationary phase. And we use reversed phase chromatography, which means that we will select a mobile liquid phase that is polar, and the stationary phase in our column is non-polar. And in the dissolution theory, there's an easy principle that says like dissolves like. So polar molecules, they like each other, and non-polar molecules, they like each other, but there's less affinity between a polar and a non-polar molecule. And so if we have a stationary phase that is non-polar and a mobile phase that is polar, and we add a mixture in the beginning of the column, then we will have the different compounds in that mixture that will have a different polarity. And those that are the most polar will stay most of their time in the polar mobile phase, while others, in this example, it would be compound A, is certainly less polar than compound C. So if it's less polar compound A, that means that it will have more affinity for the non-polar stationary phase. And
Bart,
all
if I can just
yes,
shortly,
yes.
because the translator, especially with the chromatography, has
Oh,
some
sorry.
issues of translating. So if you could speak a little bit slower, that would be appreciated. Thank
Yes,
you,
yes.
Bart.
I'm glad you tell me. I understand it's not so, but this time I didn't type my entire text before giving the presentation because I did not have time to do so. But maybe I will just do a short recap for everyone then. So two phases. The stationary phase in our case is not polar, and the mobile phase is a polar liquid solution. And so each molecule in the mixture that we will inject, has its own polarity and will have more or less affinity for the stationary non-polar or the mobile polar phase. And so we can separate the molecules in the mixture because they will spend more or less time locked onto the stationary phase, and thus so not moving in the column, while others will spend more of their time in the mobile phase, and they will advance more quickly in the column. And so in this system where the stationary phase is not polar and the mobile phase is polar, the most polar molecules will spend most of their time in the mobile phase, and they will leave the column first. And then next is the slightly less polar molecule B, and the most non-polar molecules A, they will spend more of their time in the stationary phase, and they will leave the column last. And this is also represented on the right part of the slide. So these little bumps represent concentrations. In this case, A is the most polar one, and it spends, let's say, most of the molecules A are in the polar mobile phase. Only a few of them will get attached to the non-polar stationary phase. And so the molecules of type A will move quickly through the column. For B, it's the opposite. We see that more, the area here of this bump is larger than the area of this peak. And so what is below the line is the concentration in the stationary phase. B is more or less non-polar. It will spend a lot of time in the stationary phase, meaning that it will take a lot of time to travel through the column. And if we have a selection of the stationary phase and the mobile phase that is well suited, and that depends a little bit on the molecules that we try to separate. If this combination of mobile and stationary phase is well chosen, we can separate molecules within a mixture. Of course, I think it's logical that the more A and B are different, the easier it will be to separate them. And then what is indicated in this right picture, not on the left one, is that we need a detector. We need something, some tool, and there are quite a lot of them, to show when a molecule is leaving the column or not. And in this case, the detector that we use is a mass spectrometer, but you can also use other types of detectors. Depending on the type of detector, you can gain some information about the molecule or you cannot. That depends a little bit from one detector to another. That would lead us too far. But basically the result is a signal like that, what is called a chromatogram, where you have no signal when no molecules are leaving the column. And then at some point in time, so there's a time axis running from the top to the bottom. At some point, molecules A are leaving the column, and there's a signal indicated by the detector. And then again, no molecules leave the column. That's the time between A and B, and then B leaves the column as well. And if you choose wisely, you can separate all the molecules that you want in the mixture. I hope now it was clear for everyone who had to follow in Ukrainian. So that's the idea. And it allows for a first indication of the molecule, because the time for a certain procedure, the time where a certain compound leaves the system is indicative for the presence of that compound. So the same molecule will always leave at the column at the same time, which is called the retention time, if you don't change the procedure. So if you know RDX leaves the column at 3.5 minutes, if you have a molecule that leaves at 6 minutes, you're sure it's not RDX. If you have a molecule that leaves at 3.5 minutes, it can be RDX, but you cannot be sure if you don't go a little bit further in the analysis. This is the tool that we have, so it's quite an old one. We're getting a new one, so the procedure has been launched, which takes more or less 20 years in the military. Waters is the producer of the tool. This is the name. It's not so important. The mobile phase we use is quite complicated because we also use it for methods that use TATP. And we usually don't change the mobile phase a lot. So it's a combination of three liquids: water with some ammonium chloride in it, methanol, and then some isopropanol, because the use of isopropanol allow to decrease a little bit the limit of detection. And we have a flow rate of 0.2 milliliters per minute. That's the mobile phase. It's all polar molecules, so it's clearly a polar mobile phase. Then the next, of course, is the sample. So in the preparation of the sample, we take 900 microliters of the extract of each soil. And to that, we add 100 microliters of an internal standard. The use of that internal standard will become clear. And so we have 1 milliliter of sample here, of which 90% are the extract solution and 10% is the internal standard. We inject that in the system, of course, at some point. Important is that we prepare 2 vials per sample. So that gives us the reproducibility, and if someone makes an error, we will discover it. And we also do 3 injections per vial, also to verify if everything is running smoothly. And so that gives us 6 results for each of the extract solutions. So that means that if a soil has been extracted with the mechanical shaker and the sock sled, it gives us 12 points for that soil and a specific compound. The column in this case must be, as I said, a non-polar column, so it's typically a C18 column. We heat it up to 40 degrees, constant temperature, and we have a total runtime of 16 minutes, which is quite short, I think, so it has been optimized in that way. I think that's basically it on this slide. And so this is the first result. So these are the typical retention times. The DNB is our internal standard and the 3 compounds of interest. And so if, as I said, if we have a peak at one of these, the 5.2, we always have it, of course, because we add the internal standard to the solution. But if we have a peak at 3.6, 7.5 or 9 minutes, we have an indication that one of the energetic compounds might be present. Now, other compounds might leave the column at the same time. And so we do an additional analysis with our complicated detector, which is a mass spectrometer. Now, I have a couple of slides with complicated pictures. I will not go too much into detail. I'm not a specialist either, but the first step in the mass spectrometer is the creation of ions. We have to make ions, and then we can accelerate and analyze those ions. And so the 2 types of ionization that are used in our tool are the APCI and ESI. So APCI stands for atmospheric pressure chemical ionization. So atmospheric pressure, meaning you don't need to make a big vacuum. And chemical ionization means that we create ions thanks to a chemical reaction. It's a kind of ionization that is called soft, typically, because we will have the molecules as such transformed into ions, but we will not create a lot of fragments with it. And so the principle it's quite complicated, but basically in yellow we have the output of the LC system. We have some carrier gas, usually nitrogen, and then we create droplets. There's a hot temperature here, so temperature is high, and that leads to desolvation. So it means that the methanol in our case and the mixture methanol isopropanol water is evaporated, and so we basically will remove the solvent and we will have the analyte molecules, and then these pass through a zone where a plasma is created by having a high voltage. And then there's a lot of complicated chemistry, even physics going on, but at the end of this process we create ions. And these ions usually are the analyte with an additional proton or an additional electron to have negative ions, for example. And these ions can then be analyzed in the next step of these masked spectrometer. There's a second possibility in our system to create the ions, and that is electrospray ionization. It's in principle quite different from the previous step, but it requires more or less the same tools. We need to have a nozzle, we need to create droplets, we need to have a high voltage. So all these compounds are coming back in both systems. Now here the physics are completely different. We don't have a plasma, we don't have any chemical reaction. We just have droplets that have been positively charged. And again, because the temperature is high, the solvent will evaporate and the droplets become smaller, but the charge on the droplets does not change. And at some point, there's so much, in this case, positive charge on the droplet that it explodes because the positive charges, they will repulse each other. And so we can create smaller droplets where the same process can happen again. And at the end, we will have our analyte, no solvent anymore, but there's still a remaining charge. We have created ions. What was the aim of the first part of any MS system? These two systems have a completely different physics or chemistry behind them, but they have a lot of parts in common. And so the waters, the tool we use, has a system that allows to switch very easily from one to the other. So it's basically a combined multi-mode ionization system where you can quickly switch from one type to the other. And so we use ESI for some of the compounds and APCI for some of the other compounds. And then the next part of the mass spectrometer is also quite complicated. So I also have a couple of slides with some basic theory of how it works. If it's not interesting or you never have to deal with it, okay, but I think it's always nice to have at least a small idea of some of the parameters that you can change in the system. So the mass spectrometer it basically looks like 4 rods in metal. And this is another view. So A, and B are the rods. And these rods are placed under different high tensions. And that electrical tension is for one part a constant value that we will call U. And it has a variable a signal with a certain frequency omega and a certain amplitude V. And so the 2A rods are submitted to the same electrical tension, and the B rods are submitted to the same as well, but it has a different sign than the A rods. And so we create a complicated electrical field between all these rods. And so from these ion source, we produced ions. These ions are accelerated between the ends of the rods. And so they are moving as ions with their electrical charge. They are moving into this complicated electrical field. And most of them, they will end up somewhere on one of the rods. Only some of them will have a trajectory that leads them through the rods without touching them, and only these that travel safely along the rods will be detected. And so by playing with the parameters in this system, the U, the V, and the frequency, we can select which ions will be detected and which ions will just end up on one of the rods. It's quite complicated, the theory behind it, but basically this kind of system is characterized by a parameter A and a parameter